welcome back, ladies and gentlemen. This is data analysis, the second part, and we can start now with chapter 8. So, advanced statistics, and you see here the topics: point estimates, sampling distribution, confidence intervals, hypothesis test. So, what we do here first, we will start with the three topics: point estimates, sampling distribution, and confidence intervals. And the remaining topic, I believe I will put into another video. But before that, also, let's take a look at what we have just done in chapter 7. So let's see chapter 7 for a moment, and here we have it. So what we looked at was how to obtain and sample data, then also the measures of center, the variance, and the relative standing, and then normalization of data using the Z or Z score. And we finished with the empirical rule. So let's take a very short view at it. So we can define the population as the entire pool of subjects of an experimental or model, and then we get the parameter, and we can estimate the parameter taking sample, right? So we will take a sample of the population, and what we get is now an estimate, and that is what we call statistic itself. Now we can define statistic as a numeric measurement describing characteristics of sample, and you see here the subset of a population is the sample. We obtain and sample data. Obtaining data, we can have two ways: experimental and observational. Observational is the straightforward one, without any changes, without any experiment, as it says as well, just looking at something. And then in experiment, we have the so-called control and the experimental groups. And first, the control group is exposed to a certain environment and then observed, and then the experimental group is exposed to a different environment and then observed. Continuing, we have just had a few examples about user exposed, you see, and then we created a data table. We could also regard it as a data frame, and then we actually did some more work here to come to probability sampling, and the simplest probability sampling we call the random sampling itself. So, random sampling. There are the following three suggestions from a data team. For example, separate users based on location and separate users based on time of the day, and make it completely random. Now, we have a sampling bias when the way of the sample is obtained systematically favors another outcome over the target outcome. Specifically, we are at risk of introducing a confounding factor into our analysis. And the confounding factor is a variable that we are not directly measuring, but connects the variables that are being measured. And here we have the problem of sampling bias and confounding factors as well. Okay, now suppose we are interested in measuring happiness levels of employees, and we discovered that the gender split is 75 to 25% in the company, 75 men and 25% women. Now, a simple random sample where everyone has the same chance as everyone else is very likely to drown out the voices and opinions of minority population members. Therefore, it can be okay to introduce such a favoring system in your sampling statistics measures. Okay, measures of center. So we got the arithmetic mean of data set, right? Here we also introduced how to do it as a program. We also got the median, and and then what we got is the median is less sensitive to the outliers. And then we continued with this friend example, and we got the median as, again, and the mean as well, and then we move forward to measure the variation. And the range tells us how far away the two most extreme values are. This is most useful in scientific measurements or safety measurements as well. And then basically here, most commonly used measure of variation is the standard deviation that measures how much data values deviate from the arithmetic mean. So we got through the calculation. Also, here, and we got the standard variation of 425. And here we also plotted these numbers. So the green line and the red line are here. So actually the blue line is the center drawn at the mean, so it is 789. The red line near the bottom is drawn at the mean minus the standard deviation, so 425, so it's 364. And then finally the green line towards the top is drawn at the mean plus the standard deviation, so it's 789 plus 425, as you see here as well. And that is a green line, what we have here. Now, note how most of the data lives between the green and the red lines, while the outliers live outside the lines. There are 3 people who had friends count below the red line, and 3 people you see here above the green line. It's important to mention that the units for standard deviations are the same units as the data units. So we would say that the standard deviation is 425 friends on Facebook. Okay, now the coefficient of a variation is defined as the ratio of the data standard deviation to its mean. This ratio is a way to standardize deviation, which makes it easier to compare across data sets. So this is what we also learned. And then when we combine both the measure of center and the variation to create the measures of relative standing. The measure of variation measure where particular data values are positioned relative to the entire data set. And now we actually learned the z-score or z-score. The z-score is a way of telling us how far away a single data value is from the mean. To calculate it, we need the x is the data point, the x bar is the mean, and the s is the standard deviation. And we went through this calculations, and we got a data table, and then these data points are on two different dimensions we got. So let's look at them. We could normalize them. And here we got the correlation coefficients. We know that it will lie between -1 and 1, and the strongest correlation is -1 or 1, and the weakest is 0. We already know how this works, that's why I'm not explaining it any longer. We use pandas to get the correlation coefficients, and in the data frame we get 1 and 1 because of in this diagonal they are the same, and -20, -0.21, and so not that high is the value, that is the correlation is not that strong. In the empirical rule we remember about 68 is percent, so 34.1% and 34.1% is one standard deviation far away from them. Middle, or in that way the arithmetic mean, and then we got plus 13.6, so in this way it's 95%. So if you add all them together, and then 99.7% if you got the 3 standard deviations, or 3 sigma deviation. And we calculated this empirical rule, and we got at the end to that point. So this was it, and now we can continue with point estimates. But again, the key topics in chapter 8 are the following: point estimates, confidence intervals, the central limit theorem, and hypothesis testing. Now, recall that in the previous chapter we mentioned how difficult it is to obtain the population parameter. So we had to use sample data to calculate a statistic that was an estimate of parameter. When we make these estimates, we call them point estimates. And the point estimate is actually an estimate of a population parameter based on sample data. We use point estimates to estimate population means, variances, and other statistics. To obtain these estimates, we simply apply the function that we wish to measure for our population to a sample of the data. For example, let's assume that there is a company with 9,000 employees, and we are interested in ascertaining the average length of breaks taken by the employees in a single day. As we probably cannot ask every single person we will take a sample of 9,000 people and take a mean of the sample. This sample will be actually our point estimate. So the Python code will be broken into 3 parts. We will use the probability distribution known as Python distribution to randomly generate 9,000 answers to the question, for how many minutes in a day do you usually take breaks? This will represent our population from chapter 6 actually, advanced probability. So please remember that the Python random variable is used when we know the average value of an event and wish to model a distribution around it. Now, note that this average value is not usually known. We have to calculate it to show the difference between our parameter and our statistic. We also set a random seed in order to encourage reproducibility. So now reproducibility, this allows us to get the same random numbers each time. So we will take a sample of 100 employees using the Python random sample method and find the point estimate of the mean. Note that this is just over 1%. I have to start at the same time spider this time. So just over 1% of our population. Now we will compare our sample mean, the mean of the sample of 100 employees, to our population mean. Okay, so let's take a look at what we need here. I need a new untitled document, actually a program. And let's see. Okay, so let's see the code itself. Import. So import numpy as np, import pandas as pd, and from scipy so scipy, right? Import stats, and from scipy stats method import Poisson and np, so NumPy random method and seed function, and we got 1, 2, 3, 4 here, just as we explained the reason. So again, also set the random seed in order to encourage reproducibility. So this allows us to get the same random numbers each time. So we got the log breaks. variable into stats. So stats, Poisson, and RVS. So, oops. RVS, and let's see what RVS exactly is. So RVS is random variates, and we can also see what we have to create. So loc is location parameter, and that is 10. The mu is shape parameter, which is 60, and that's about the 60 minutes break time, and the size is right now 3000. So this represents 3000 people who take about a 60-minute break. Now, the long breaks variable represents 3000 answers to the question, how many minutes on average do you take breaks for? And these answers will be on the longer side. So let's look at the visualization of the distribution as follows. Probability density function, isn't it? It's pandas series, and actually Poisson goes with PMF as I remember. So probability mass function, long breaks, and histogram. Yeah, so not history, but histogram. And that's it. Let's try to run it this time. Hopefully it runs very well, very well. So it runs well. We can see the plot here as well. Great. So we can see that our average of 60 minutes is to the left of the distribution. So to the left of the distribution. Also because we only sampled 3000, our balls are at their highest at around 700 to 800 people. Now let's model the 6000 people who take on average about 50 minutes break. And let's use the Poisson distribution again to simulate the 6000 people. So this time, short break, stats, Poisson, and Poisson RVS. Loc is 10 again, mu is this time 15, so the shape parameter and the size is 6000 as we talked about it. And again we need to plot it, so PD series short breaks and hist done. Okay, let's try to run it this time, and we get the 2, and if we get rid of this here first, and we just run the last one, so we get it here. So we have the distribution for the people who take longer breaks and a distribution for the people who take shorter breaks. Again, note how our average break length of 15 minutes fall to the left hand side of the distribution, and note the tallest bar is now about 1600. So I'm not sure if I can. Yeah, I can make it larger. So it's about 1700 maybe. And we can continue now. Breaks. And np concatenate. This is actually what we have just done. Okay, so long breaks and short breaks. And then all we need to do this time is PD series and breaks. And again here histogram, and let's run it, and we got the two together, so we can see that we have two humps on the left. We have our larger hump of the people who take around 15 minutes break. And on the right hand, the smaller one, this is it. So this one here, a smaller hump of people who take a longer break. So later on, we will investigate this graph further. We can't find the total average break length. So if you would like to see it, so you can find the total average break length by running the following code. So break mean, but I believe that I need to print this out, and I'm going to get rid of all the plots now. Let's run it again, and here we have what I just mentioned. So the 39 minutes in our, is our parameter. So 9.999 is our parameter. Our average company break length is about 40 minutes long. Now remember that our population is the entire company's employee size of 9,000, and our parameter is 40 minutes. In the real world, our goal would be to estimate the population parameter, because we would not have the resources to ask every single employee in a survey their average break length for many reasons. Instead, we will use a point estimate. So to make our point estimate, we want to stimulate a world where we ask merely 100 random people about the length of their breaks. So to make our point, we want to stimulate the world of 100 random samples, as I mentioned. Okay, so we need this time sample breaks and np random choice and random choice, and a is breaks, and size is 100. Taking a sample of 100 people, 100 employees. Okay, now let's see, print the breaks mean minus the sample breaks mean. And let's see what we got. So we got 0.6994, which is actually really not bad. This is really interesting because within only 1% of our population, so 100 from 9,000, we were able to get it within like not even a minute difference, right? So not bad in that way. So here we calculated the point estimate for the mean, but we can also do this for proportion parameters. By proportion, I'm referring to a ratio of two quantitative values. So let's see. Also our file, you see that here, this is what we have just done. And I continued here. And this is what we got. And we got also the mean, and now here we got a result of 0.69 minutes, which is very good, as I mentioned, since we have just a little bit more than 1% of the entire population. Now, let's suppose that in the company of 10,000 people, our employees are 20% white, 10% black, 10% Hispanic, 30% Asian, and 30% identify as others. We will take a sample of 1,000 employees and see whether the race proportions are similar. So let's see. So all I need is this here. Actually, I can continue here. And here. Let me see if we are done, and I believe that we have a problem here. No, it's not. That's completely correct. Good. Okay, now employee races represent our employee population. For example, in our company of 10,000 people, 2,000 are white, 3,000 are Asians, and 10,000 are Hispanic, and so on and so on. So, okay, now let's import random, and we take a demo sample, random sample employee races, and only 1,000, so sample value is 1,000. And for race in test demo sample, print race plus proportion estimate, and print demo sample count race divided by 1000. Okay, let's try to run it. Not sure if everything is going to be fine. Okay. So let's see what is wrong here. For race in sats, not tests, sat. Okay, here we go. Then well done. This is it. Okay. So what we got is actually the race proportion estimates are very close to the underlying population's proportion. For example, we got 10%, 11.2% for Hispanic in our sample, and the population proportion was actually 10%. Now, sampling distribution. Here I need to take next step, and now it's completely done, right? You see we get always another number, yeah, but again very near to that what we actually have. Sampling distributions is the next large topic, so let's move forward to sampling distribution. Now in chapter 7, basic statistics, we mentioned how much we love it when data follows the normal distribution. One of the reasons for this is that many statistics or many statistical tests rely on data that follows a normal pattern, and for the most part, a lot of real-world data is not normal, right? That's been actually we know. Take our employee break data. For example, you might think I was just being fancy creating data using the Poisson distribution, but I had a reason for that. So we actually had a reason for that, and we specifically wanted non-normal data. What we got here as well, as you see it here. So let's also continue our example over there. So PD data frame breaks and hist bins 50 range is equal 500. So let's get rid of these things as well. Okay, all the other parts is done, so let's run it. Okay, invalid syntax. I forgot the comma, and there it goes. Great. So now, as you can see, our data, there we go, is definitely not following a normal distribution. It appears to be bimodal, which means that there are two peaks of break times at around 25 minutes. Here we go, right? And around 70 minutes. As all data is not normal, many of the most popular statistics tasks may not apply. However, if we follow the given procedure, we can create normal data. Well, let's see. So first off, we will need to utilize what is known as a sampling distribution, which is a distribution of point estimates of several samples of the same size. Our procedure for creating a sampling distribution will be the following. Take 500 samples of the break times of size 100 each and take a histogram of these 500 point estimates revealing the distribution. The number of elements in the sample, so 100, was arbitrary but large enough to be a representative sample of the population. The number of samples we took was 500, so also arbitrary, but large enough to ensure that our data would converge to normal distribution. Let's see how that would work this time. Okay, spider again, and let's continue. Let's get rid of this here. Do we need this data frame again? I believe not. Yeah, not now. We will update it anyway. So point estimates. This is going to be a list. 4 acts in range, and sample size is now 500. Sample NP ran NP random choice. A is breaks and size is 100. Now we need to append them, so point estimates append, we create just a list, sample mean done. And PD data frame point estimates and histogram. I believe that this part would be out, so let's try to run it. This is what we get now. And what if it's inside the for loop, which I doubt that it would be inside, but in the book it's inside. So this is it, what we get. Obviously something is going to be wrong, as I see here. Well, let's stop it. Keyboard interrupt, nothing happens. You see that the data frame must be outside, otherwise it's not going to happen what we need. Okay, so you can look at the distribution of our sample means. This is it. And the sampling distribution as the sample mean appears to be normal, even though we took data from an underlying bimodal population distribution. It is important to note that the bars in the histogram represents the average break length of 500 samples of employees, where each sample has 100 people in it. In other words, sampling distribution is a distribution of several points estimates. Our data converge to a normal distribution, as you see here. because of something called the center limit theorem. So central limit theorem, which states that the sampling distribution, so the distribution of point estimates, will approach a normal distribution as we increase the number of samples taken. What's more, as we take more and more samples, the mean of sampling distribution will approach the true population mean, as we also can see it. So print, break, do we have the break means? Yeah, here we go. Mean minus NP array point estimates mean. Let's see. So yeah, here we go. That is, the difference is going to be just 0.42 minutes. This is actually a very exciting result because it means that we can get even closer than a single point estimate by taking multiple point estimates and utilizing the central limit theorem. In general, as we increase the number of samples taken, our estimate will get closer to the parameter or to the actual value as well. Okay, so let's continue now with the confidence intervals. So what point estimates are kind of okay. Estimates of a population parameter and sampling distributions are even better. There are the following two main issues with these approaches. Well, the single point estimates are very prone to error, so due to the sampling bias among other things. Then and taking multiple samples of a certain size for sampling distributions might not be feasible and may sometimes be even more infeasible than actually finding a population parameter. Now, for these reasons and more as well, we may turn to the concept known as the confidence interval to find statistics. A confidence interval is a range of values based on a point estimate that contains the true population parameter at some confidence level. Confidence is an important concept in advanced statistics. Its meaning is sometimes actually being misunderstood, misconstructed. Informally, confidence level doesn't represent the probability of being correct. Rather, it represents the frequency that the obtained answer will be accurate. Now, for example, if you want to have 95% chance of capturing the true population parameter using only a single point estimate, you have to set your confidence level to 95%. Higher confidence levels result in wider, larger confidence intervals in order to be more sure. Now, calculating a confidence interval includes finding a point estimate and then incorporating, so putting a margin of error to create a range. The margin of error is a value that represents our certainty that our point estimate is accurate and is based on our desired confidence level, the variance of the data, and how big our sample is. Now there are many ways to calculate confidence intervals. For the purpose of brevity and simplicity, well, let's look at a single way of taking a confidence interval of a population mean. Now for this confidence interval, we need the following things. A point estimate. For this, we will take our sample mean of break lengths from our previous example, and then an estimate of a population standard deviation, which represents the variance in the data. And this is calculated by taking a sample standard deviation and dividing that number by the square root of the population size. And then number 3 is the degrees of freedom, which is the -1 sample size set here. So -1 sample size. Obtaining these numbers might seem arbitrary, but there's a reason for all of them. However, again, for simplicity, I will use the previous Python modules, and we can calculate our confidence intervals. So confidence interval, and then demonstrate its value. Let's do it. The histogram I will close now. All of them we have. I'm not sure if we need any more at the moment. Anyway, import math we need. Then sample size we create 200. We set 200, and sample. Do we have it here? Random choice. A break size is now sample size. So actually this is completely correct. So here we go. This is it, and this is sample size. So all we need to do here just add here sample size, which is actually done. So that's it. Then let's take another look. Now the sample mean we already know, right? Sample mean is sample mean. Good. So the sample mean of the break length is that. We could also take a view of it. Then sample standard deviation, sample STD EV, sample STD, and let's also print this part. STDVE, okay, and then let's continue again. Now sample mean is good, and I'm going to take this as well. Sample standard deviation is standard deviation is okay. Then let's check the sigma sample standard deviation divided by mat, and we remember like square root, right? sample size sigma, sorry, not E. That is the population standard deviation estimate, and that's T interval. And now alpha is going to be, you see it here, how to use. So alpha of float, that is the confidence interval set to 0.95. Then the degrees of freedom is -1, sample size -1. Then lag is sample mean, and scale is sigma. So interval and print interval. Let's try to run it. Okay, we have a problem here. Where? Line 36. Size I didn't make. Now it's correct. God damn it. Got it. Okay, now sample mean is 40.78. Sample standard deviation is 22.61, and we got the two values. So we got 36.29 and 45.26. So to reiterate, this range of values from 36.29 to 45.26. Here we go. We got a different value, but it doesn't matter. So the point is that represents confidence interval for the average break time with 95% confidence. And we already know that our population parameter is 39.99, and note that the interval includes the population mean of 39.99. I mentioned earlier that the confidence level is not a percentage of the accuracy of our interval, but the percent chance that the interval will even contain the population parameter at all. So to better understand the confidence level, let's take 10,000 confidence intervals and see how often our population mean falls in the interval. First, let's make a function. So here we go. Let's make a function that makes a single confidence interval from our breaks data. That is it. Def make confidence interval sample size is 100, as we know. Sample, actually I think we can just copy this here. sample NP. Yep. Now the next one is the standard deviation and also the sigma. So everything should be the same. So sigma square root, okay, everything is the same. Population standard we get now. And then return, and this is it. So all I need to do is now return and stats t interval for 95%. Degree of freedom is sample size -1, sample mean is the log, and scale is sigma. Now that we have a function that will create a single confidence interval, let's create a procedure that will test the probability that a single confidence interval will contain the true population parameter. So here it is. Take 10,000 confidence intervals of the sample mean, count the number of times that the population parameter falls into our confidence intervals, and the output, the ratio of the number of times the parameter fell into the interval by 10,000. Okay, let's do it. Times in interval for I in range, and now it's 10,000 confidence intervals, and interval make confidence interval, and if 39.99 is larger than or equal, interval, the first interval, and 39.99, sorry, it's less than interval, one, so then times in interval and plus 1. So we had 1 by each cycle. And then what we need after that is to print times in interval divided by 10,000. So how many times it happens? Let's see. Okay, and what we get is 94.72, even better than in the book it's described. Yeah, even better than in the book it's described. Success, we can see that about 95% of our confidence intervals contain our actual population mean. Estimating population parameters through point estimates and confidence intervals is a relatively simple and powerful form of statistical inference. Now we can take a quick look at how the size of the confidence intervals changes as we change our confidence levels. We can calculate different confidence intervals. For multiple confidence levels, and look at how large the intervals are by looking at the difference between the two numbers. Our hypothesis will be that as we make our confidence level larger, we will likely see larger confidence intervals to ensure that we catch the true population parameter. And for that, what we need is for confidence in 0.5, 0.8, 0.9, 0.95, and 0.99 confidence intervals again, stats t. So again, the same. And length of interval is going to be a rounded number of confidence interval the 1 and confidence interval 0. And then now what we need is print confidence 0 has a interval of size one format confidence and length of interval. Okay, this is still in 4, so let's try to run it this time. Okay, here we go. Let's get rid of this. Let's move it out. Let's see how it works. Okay. Let's try to run it again. Degree, yep, length, interval, this goes up. Okay, then the length and print goes here and format comes here up. Does it work this time? Yep, it works this time. Okay, before that I don't know exactly why it didn't work, but now it works perfectly, no problem. So once again, our hypothesis was that as we make our confidence level larger, we will likely see larger confidence intervals to ensure that we catch the true population parameter, and this is exactly what happened. So the interval became larger and larger, we can see that as we wish to be more confident in our interval, our interval expands in order to compensate. Now, after this, we can take our concept of confidence levels and look at statistical hypothesis testing in order to both expand on these topics and also create even more powerful statistical inferences. So what we have just looked at, let's take them again. The point estimate we went through with a bimodal graph, right? And then we could basically merge them in the sampling distribution, and we talked about the confidence intervals as well. The next what we talk about is the hypothesis test. So I think that this time let's make a break and we can continue with the hypothesis test. Thank you very much for your attention and see you for the next video. Bye.